Hello guys, so in this video, the idea will be to understand how different languages are executed. okay so in the previous video we understood concurrency, parallelism, cooperative scheduling, preemptive scheduling, user threads, kernel level threads. And I have also shown you different threading models. Now in this video we will connect all those concepts in three programming languages, that is C++, Python and Go. So the question that we are trying to answer is simple. okay when we are writing a C++ or a Python or a Go, how does the code finally reaches to the machine, okay or to be more specifically to the CPU core. okay because from the outside, all three looks same. So if I show you the actual code, all of this looks same, right? We write a program, we run the program, we get some output. But internally the execution flow is very different. okay so C++ usually takes the shortest path. So here in this HTML page I have just created an execution flow for all these three languages. So as you can see, like, there are more section in C++, sorry, in Python and Go, as compared to C++. So C++ usually takes the shortest path to native machine execution, whereas Python goes through some bytecode, then to interpreter, then to runtime objects, and then it has its GIL model. okay Whereas in Golang compiles to native code, but also brings a powerful runtime scheduler. As you can see here. okay Now this scheduler basically schedules those Goroutines into multiple OS threads. Now, and like, to understand all this execution flow, it is pretty important because it will help you understand how you can create your own distributed algorithms. And also I'm planning on creating another video, where we can understand like how to remove the limitations of Python GIL, by writing a C code, and how to bind them with your Python code. I will show that in the next video. okay so yeah, so before we compare the languages here, so we should remember the common path. Every program eventually gets executed in the hardware. So I'll just open up a whiteboard. Let's go here. Let's make some room here. So just have this in mind. Every program gets executed on your hardware. okay Now the way they goes inside the hardware are pretty different among all the languages. Now at the top we will have a source code. As you can see here, we have source code for three different languages. Then depending on the language, it may go through the compiler, it may go through a interpreter. There is a bytecode VM also, which is for Python, and then there is a runtime scheduler, which is for Golang. Then after all these layers, then the operating system comes into play. The OS takes all those instruction, it create processes, it manages memory, it also schedules the threads that we want to create, it also handles syscalls. It also maps the runnable work to the actual CPU cores. So, and then only we finally execute all this instruction on our CPU. So on a broad level, so we have some stacked up layers here. So on a so the general layers in every programming language, are first your source code. Then there is a compiler, and interpreter. Okay, then there is runtime. Okay, then there is your OS scheduler. Okay, which we have seen in our previous lecture, the CFS scheduler that we have in our operating system. Okay, then we have kernel level threads. Okay, now these threads are very low level threads that directly gets mapped to your CPU cores. Okay, and then we have like memory blocks, okay, where our RAM and caches comes into play. Then also inside the core we have registers. Okay, and then we have the actual alias which performs the computation. Okay, so on a general sense, these are the layers uh, where every programming language goes, okay, to gets executed. Okay, so this is the mental model that we are going to use. Okay, and yeah, so let's start with C++. Okay, so let's focus upon C++ here. Okay, so in C++, okay, when we are writing a C++ code, okay, we usually compile it before execution, right? So there are the popular compiler being the G++, and for C, I guess there is GCC also. Okay, now the source code after compilation, as you can see here, okay, it has a build pipeline, okay, where the preprocessor in that pipeline, okay, it takes all the macros and the include statements. Okay, for example here in this code, okay, I have this threading library, and also I have this vector library. Okay, so the preprocessor brings in those declaration for creating an aggregate of all your program. Okay, basically you're importing them, right? But in order to make a actual executable, so you have to bring in all stuff, right? Now then after it has brought up all the stuff, okay, then the compiler converts the C++ code into a assembly code. Okay, and you can think of it's a low level intermediate machine code, okay, that directly interacts with the machine. Okay, then the assemble like the assembly code, once it is done, okay, it then creates some file objects. Okay, so that is this part. Okay, then there is a linker layer also, okay, which connects all those file objects to actual runtime libraries. Okay, and it brings in the final executable file. Okay, so if you are in Windows, okay, you must have seen .exe files. Okay, in shell, like in Linux, you basically compile it to a file that doesn't have that doesn't have an extension, but uh, if you see the properties of it, okay, the file properties, you will find that it's a executable file. Okay, cool. So on a rough note, okay, for C++, okay, so we have our source code. Okay, then we have our preprocess layer. Okay, then we have our compile the compiler layer. Okay, then we have our assembly layers. Okay, and then we have a linker layers. Okay, and then we produce the native executable depending upon the platform where you are compiling it. Okay, so native exe. Okay, now when we run the executable file, okay, so let's zoom in here a bit. Okay, so when we are running that executable file, okay, that time our runtime model comes into the play. Okay, so at that time, so basically when we run that executable, okay, the OS loader maps that binary, because your executable is a binary file, right? So it maps that binary to our memory model. Okay, so that memory model is, so till here everything is happening to your code. Okay, so you have the controller. Now at this point, this is where your OS takes care of the things. Okay, so in this code, as I'm creating some threads, okay, So when I'm creating those thread, they are mapped to my OS threads, okay, which on Linux are backed by our P threads, okay. So the POSIX threads in Linux, okay, um, POSIX threads, okay, this is a threading library, okay, that creates an abstraction over our OS threads, okay. So the C++ code has the ability to directly create a P thread, okay, which is the direct abstracted version of your OS thread, okay. Now all these OS threads, okay, are taken up, okay, by your OS, and um, they run inside a process, okay, where the kernel queues up all those threads, okay, and it performs on its own, like its own file operations, any network operation, okay. There is also memory mapping involved. Let's say your code does some pointer allocations and all that, so getting those pointers, there are some hashable calls also include, okay. So all those mapping, OS takes care of that, okay. Now one thing to observe here is, okay, we do not have any GIL here, okay, which basically means there are no locks over our code, okay, as compared to what we have seen in Python, okay. And if you guys are coming from, let's say, OCaml or Ruby background, you guys will also feel there is a GIL lock, okay. But in low level code like C++, like C++, Rust, okay, okay, maybe Java, okay, they do not have any GIL concept, okay. So it is the programmer who writes the code in such a manner so that there will be no race condition or starvation or any live log kind of a situation, okay. So cool. Now in C++, the memory management and the synchronization, that's why are more manual, okay, because the programmer has to do it, okay. Cool. Now as you can see here, okay, so we write our code, okay, we convert it to executable, okay. Now the runtime of for C++ code, okay, that directly talks to the OS, okay, to execute its program, okay. Then when it's get executed, the OS takes care of all the threading instruction, okay, and it creates those threads and maps it to our CPU core, okay. Cool. So this is kind of the shortest path, okay. So you just compile your code once and just run the executable. Now whenever your executable is running, it directly talks to your machine, okay. So C++ is having the shortest path, okay. Cool. Now let's see for Python. Okay, I'll just draw this. Let's go with Python, okay. Now in this Python section, okay, I'm doing the same amount of code. So there is some HTML rendering issue is happening, okay. So the actual code does look like something like this, okay. So I have a worker function, okay, and these worker function are invoked multiple number of times by my thread pool executor, and I will come to this code, but just understand that when we are coding in Python, okay, so Python is basically designed for developer productivity so that they can ship out the code faster as compared to C++, because in C++ we have to take care of all the things like the memory management and all that, okay. So the developer has to do it, whereas in Python it automatically does that for us. So when we write a Python file, okay, as like this here, okay, so it we usually save it with .py extension, okay. So till this layer we have our Python, okay. Now when we try to execute it, okay, so it is executed by CPython, okay. Now in CPython, so it is the standard Python implementation, okay. And the source code first gets compiled into a bytecode version, okay. So as you can see here, this is my source code, okay. So there is a parser layer involved, okay, which reads the Python code, okay, and it converts to .pyc files, okay. So if you guys have seen pycache directory being created when you execute your Python code. Okay, so that is basically your bytecodes are being generated there. Okay, and it also act as a cache, because whenever you are relearning your Python code, okay, it just um, it's just do some diff changes in that pyc file so that uh, it can compile faster. Okay, now this bytecode, okay, this bytecode is not same as the assemble code that we are generating in C++. Okay, this bytecode is still a low level abstraction, but this is kind of the language that the Python interpreter understands. Okay, so just keep that in mind. The bytecode is not a machine code for the CPU. Okay, it's a machine code for your interpreter. Okay, so when you install Python, you install a Python interpreter. Okay, so the language that you are writing in Python, okay, that gets translated to a pyc file. Okay, and then interpreter reads that file. Okay, it reads that, and it checks all your instruction on how to interact with the machine. Okay, cool. So in Python, if I list out the code flow, okay, like before the machine takes over the control. Okay, so there is again your source code. Okay, then there is your parser. Okay, so and your AST instance, which basically reads all your code and converts that to pyc file. Okay, then there is bytecode layer. Okay, then there is your interpreter. Okay, now when the interpreter executes or reads this bytecode, it usually does that in a loop. Okay, maybe a while loop. Okay, then when it reads that, it sees all the instruction, where are we creating objects and all that. So there are runtime objects being created. Okay, and yeah, and after that it just launches a process. Okay, it launches a OS process, which is basically your interpreter process. Okay, in which the loop is running and it constantly reading your bytecode. Okay, now in that process, it basically like schedule all the jobs to onto the OS. So there is then CPU execution. Okay, so yeah, so the important point to note here is the CPU is not directly executing your Python source code. So whatever code you have writing here, okay, this is not directly mapped to your CPU cores. Okay, whereas in C++, we have that kind of a situation. Okay, so yeah, and so yeah, so that is why the Python has dynamic features. Okay, because the CPU is actually executing your CPython interpreter code. Okay, and the interpreter is just keep on reading and executing your Python bytecode. Okay, so all those object classes and whatever things you have written there, maybe function calls, maybe some memory management. Okay, all that is happening when the code is actually being run by your interpreter. Okay, now since Python is a garbage collector language, that also means the interpreter does some reference counting also, so that it can know like when the object has to be deleted, it can know when the object is not being used. Okay, and all that stuff. So all that heavy lifting, okay, we do not have in C++. The coder does that, whereas in Python it simplifies our life by running the interpreter. Okay, so the interpreter does all that stuff to us. Okay, so that is why Python is pretty flexible, right? So flexible. Okay, but it has the longest path to the CPU core. The longest path. Okay, as you can see here, okay, so we wrote our code, it gets compiled, it gets converted to bytecode, the interpreter reads our file in a loop. Okay, then there is a runtime model where we create the interpreter process. Okay, or to be more specific, here I have mentioned the CPython process. Okay, now within that process, whatever threads we are creating, okay, all of those threads are backed by a GIL. Okay, so there is GIL involved. Okay, so whatever process you have created, okay, so let's say this is the interpreter process. Okay, and whatever threads you are creating in those processes, okay, those are your actual p threads. Okay, so I'm talking specifically with respect to your thread pool executor. I'm not talking about async IO. Okay, so with specific to thread pool executor, you are directly creating a couple of p threads. Okay, now all those p threads are backed by a lock. Okay, uh, okay, let's get a lock picture. Okay, let's use this. And let's erase this guy. Okay, okay, this thread also is backed by a GIL. Okay, now these locks are your GIL. Okay, cool. Now what GIL means? GIL means global interpreter lock. Okay, so it is kind of a inherent mutex that every thread has. Okay, due to which whatever bytecode the interpreter is running, okay, so even if you are spawning multiple number of threads to run this function, okay, let's say this run function. Okay, so when a thread is running that function, it will take, so let's say you have multiple threads waiting to run your worker. Okay, so when it goes to the OS level, okay, since all the threads have a lock on it, okay, so the bytecode that we have produced, okay, every thread will put up a lock on this code, it will execute them. Okay, then it will go back inside the queue. Okay, let's say this is a big queue here. Okay, now since every thread is putting up a lock here, okay, a lock over your bytecode, that means no two threads can access the same bytecode at the same time, which basically means even if you are spawning, let's say, hundreds of workers, or like say you have created hundreds of threads from your bytecode, since every thread is putting up a lock upon your bytecode, okay, that means no two threads can run the same function at the same time. They have to wait until the thread that is executing your bytecode has uplifted that lock. So this is why for any kind of CPU bound work, okay, CPU bound work, okay, Python is bad. Okay, because of GIL. Okay, as you can see here. Okay, so when we are creating this model, okay, this runtime model, within this process only one thread is being executed because it is putting up a GIL log over the bytecode. Okay, now when it is executed, okay, it talks to our OS. Okay, the OS does the heap allocations, stack allocation, and all that. Okay, then it goes to the kernel where it actually creates a p thread, and that p threads get scheduled by your OS. Okay, and it gets executed over our course. Okay, so that's why Python is bad for us. Like only Python is bad for CPU bound work. Okay, but we have seen that there are libraries like OpenCV, NumPy, PyTorch, TensorFlow. Okay, all that stuff is pretty fast, right? Like how? Since we just saw like GIL is kind of creating a bottleneck for compute bound work, right? So in those libraries, okay, they are not removing the GIL, they are kind of bypassing the GIL. Okay, the way they are doing it is whenever you are creating this interpreter process, okay, and let's say you have an instruction to run something, what they will be doing is, okay, let's say here you have your main thread, okay, and say this is your interpreter process, okay. So this main thread will delegate the CPU bound work, okay, to uh maybe a C++ file, okay, or a C file, okay. So in that way, we know when we are executing C or C++, okay, they can directly talk to the machine, and they do not have any locks in them, okay. So the main thread simply delegates the work to this low level language. Let's say there is also some Rust languages are also there, okay. This we do by binding low level languages with Python, okay. So we are not removing the GIL, okay. We are basically delegating the work to those languages where where GIL is not present, okay. So that we will not face bottlenecks when we are running our actual Python code. So the Python code is actually working as a orchestrator here, okay, in order to run those low level languages, okay. Cool. So now this is about CPU bound work, okay, but there is a way when uh, GIL doesn't act much, okay. So for example, when let's say you are building some kind of a IO bound, or let's say you are writing your code for a IO bound work, okay. um let's say something like web scraping, okay, web scraping, okay, and let's say you have to write bunch of files, okay, write bunch of files, okay, without doing any heavy computation work, okay. So in these calls, okay, each thread when they will be executing the bytecode, okay, the interpreter will see that, hey, this guy is waiting for something, okay, and this is he is not utilizing the core, okay. That means I can yield its job, okay, and I can take upon the next task, okay. So in that way the interpreter runs it concurrently, okay. So that is only one time. Whenever you are doing any IO bound task, the GIL lock is removed, okay. So basically that interpreter yield the control, okay, of the thread that is executing your bytecode, okay, to other threads, okay. So yeah, here I guess I have mentioned, okay, IO may sleep or wake, okay. So that basically means for any IO bound of work, thread pool executor is nice, okay, because GIL may or may not come into that picture, okay. That depends upon how you are building your IO bound work, okay. Cool. So that's for Python. So just take the note of the GIL mechanism, okay, and just understand Python is only built for developer productivity, okay. The actual heavy computation kind of work, they are still handled by low level languages like C, C++, Rust, okay. I will not include Java, okay, because that requires a JVM and I hate that. Cool. Now let's look at Go execution flow, okay. So here we have our Go program. Okay, this doesn't look good. Okay, let's see this. Okay, we have our Go code. Okay, each of them are doing the same thing. Okay, so there are 1 million numbers. Okay, and each of them are computing this value per number. Okay, and yeah, for 1 million number they are just computing 2 times of that number plus 1 and doing a square root over that. Okay, so that's their work. Now in Go, okay, Go, as we discussed in our previous video, okay, it has a hybrid model with cooperative and preemptive scheduling. Okay, so let's create something for Go. Okay, there is Golang. Okay. Now the path from a Golang code to your actual CPU, okay, that is kind of a midway between your C++ and a Python one. Okay, so it has a intermediate path length. Okay, so Python has the longest path, whereas C++ has the shortest path. Go has somewhere in between. Okay, now Go is an interesting because it feels like we are closer to C++, okay, in execution speed, okay, but closer to Python in developer simplicity, okay, because Go code is pretty simple, okay, and there are not much concepts in Go that we have to use, whereas in Python there are so many libraries involved, right? If you compare C with Python, C is simple because there are only few things that you need to know in order to write code in C, okay, but in Python you have to understand different libraries, okay, in order to write code in Python. Okay, I'm not talking about simple stuff. Okay, I'm talking about some actual stuff, for example web scraping and all that stuff. Okay, so yeah, for Go those things are kind of midway. Okay, Go provides you the simplicity, but it also gives you that developer friendliness that you don't have to know about more things in order to uh, write code in Go. Okay, so let's see the execution path. Okay, so when we are writing Go files, okay, we save it with .go extension. Okay, now whenever we write .go files, we compile them. Okay, the compile, so there is a Go compiler that compiles it to native code. Okay, there is also linking involved where it creates some file objects and all that stuff, and after that it creates a executable, same as what we have seen in C++. Okay, now this executable, okay, this executable is not directly talking to your OS. Okay, what we have seen here. Okay, there is a middle layer which is your GMP scheduler. Okay, the GMP scheduler performs the cooperative scheduling here. Okay, so I'll just write down the broad level steps that we do in Go. Okay, so there is your source code. Okay, now in your source code, whenever you are creating Go routines, so there is a layer of Go routines. Okay, now this Go routine has multiple things. Okay, so they have their own function calls and all that. So all that happens during the compilation layer. Okay, so there is a compile layer. Okay, then there is linking involved. Okay, then there is, after linking we produce the native executable. Okay, similar to C and C++, native exe. Okay, now in the sixth step we have the GMP scheduler. Okay, what it does, I'll just talk to you. Okay, then after this GMP layer we produce OS threads. Okay, that gets mapped to our CPU cores. Okay, so by the number of steps, okay, you will see that we are kind of one step extra here. Okay, because I can actually remove this. Okay, this is kind of optional. Okay, okay, in Python we had 7 steps, here we have 8 steps, but one thing you should keep in mind that here we are creating a executable. That means all that compilation stuff we don't have to do it anymore, whereas in Python the interpreter always has to read the file from scratch from top to bottom in order to run that or in order to create that bytecode and execute it, right? Whereas in Go, once you're done with creating the executable, just ship it. That's not always the case, but assuming you have your developer environment and your production environment same, so you can run that executable in the production environment. But yeah, we'll come to that in later videos. But here what should you focus upon is this magical model, which is your runtime model in Go, which is GMP scheduler. Now GMP scheduler uh, is an acronym for G, which which is for Go routine. Then there is M, which is your OS thread. Okay. Then there is processor. Okay. Now what it does is, okay, it performs multiplexing. So as we saw here, like as we saw in our previous video, okay, so we create multiple Go routine. Okay. Then there is a multiplex layer, which is basically your runtime. Okay. Now this runtime has a queue. Okay. It loads up all the Go routine. Okay. And it maps it directly to your P threads. Okay. Or your OS threads. Okay. See, when I'm saying P threads or OS threads, these are not your hardware threads. Okay. These are just the threads which lie just above your hardware threads. Okay. The hardware threads gets mapped to your P threads. Okay. Your P threads are not mapping to your hardware, like the P threads are not your hardware threads. Okay. So let's say when I'm doing this ls cpu, okay, I'm seeing like per core I have two threads. Okay, these are my hardware threads. Okay, these are not my P threads. Okay, so if I open up my performance and basically task manager, and in there if I go to cpu, okay, you will be seeing lots of threads are being running. Okay, these are my P threads. Okay, these P threads are getting mapped to my hardware threads, which is 32 here. Okay, because I have 16 cores. With 16 cores I have two threads per core. That means with hyper threading I am getting 32 threads. So all these P threads, okay, here are mapped to 32 threads. Okay, now the execution of all those threads is pretty fast, uh, which kind of creates a situation that all these threads are being executed simultaneously, but that's not the case. Okay, as we saw in our previous video, how the OS does the preemptive scheduling, where it just time slice between different threads. Okay, uh, to run multiple threads onto the same worker. Okay, onto the same worker thread. Okay, so yeah, here just remember that whatever user level threads you are creating, or green threads or Go routines, okay, those are being mapped to one or more P threads. Okay, now this P threads gets mapped by your OS and kernel, okay, to your actual hardware thread, okay, which lie inside your core. Okay, so this is your core. Okay, cool. Now what this GMP model does is, okay, so the G here is this part, the M that you are seeing, the runtime. Okay, the runtime also requires OS thread to keep it active so that it can run its scheduling algorithm, right? So the M here is a P thread that we see. Okay, now the important concept you should remember is mapping a P thread to a OS thread uh, is always simple. Okay, because P thread is built as an abstraction of for your hardware threads. Okay, so this M thread, it basically takes all the Go routine and then one by one maps it to different OS threads. Okay, as we are seeing here. Okay, so it it is taking upon all the Go routines that I'm creating in my code. Okay, go 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 go. Okay, 3 Go routines. Okay, and it maps them, okay, to multiple P threads here. Okay, now these P threads, okay, they goes into the OS. Okay, they allocate some memory, they have their own stack space, uh, TLB tables, okay, all that MMU stuff, memory management unit stuff, okay, along with some synchronized primitives, all that is happening inside the OS. Okay, then the kernel sees that all these P threads, I have to schedule them to actual cores. Okay, and it does that mapping. Okay, now since um like as we discussed, Go is kind of midway between C++ and Python. So Go is also a garbage collected language, which also mean it does some operations of not exactly reference counting, but it has a map of all the memory units that we are creating in our language. Okay, and the end of our Go program, all that are getting cleared by our garbage collector in Golang. Okay, cool. But the point here to remember is this model. Okay, this hybrid model that Golang is using. Okay, so yeah, and as we saw in our previous video, so up to this layer, okay, we are kind of doing cooperative scheduling. Okay, okay, and from this p threads to mapping to the actual hardware threads, this is where preemptive scheduling is happening. Okay, so this is why Golang is simple as well as pretty powerful. Okay, so yeah, now let's see all of them together. Okay, so yeah, now let's compare them one by one. Okay, C++, it does ahead of time compilation, which basically means we have to compile first, then bring the executable. Okay, there is no GIL involved. Okay, the threads are directly mapped to p threads. Okay, and those p threads are mapped to your hardware threads. Okay, then there is a very simple model for CPU parallelism, but with great power comes great responsibility, which basically means all that memory management and putting proper synchronization primitives in the code. It is the job of the developer. Okay, cool. Now coming to Python. Okay, as we saw, whatever source code we are writing, okay, those are first converted to bytecode. Okay, the bytecode is read by the interpreter and it does in a looping fashion. Okay, so that's why the majority of the hard work, okay, is already done by your interpreter. Okay, so that's why Python is pretty simple. Okay, but with simplicity there are bottlenecks like GIL, due to which CPU bound kind of work is not possible by only Python code. Okay, we do some delegation to lower level languages in order to bypass GIL. Okay, whereas for any kind of IO bound task, Python is really good, because in that time the OS sees that, okay, so it is doing a waiting kind of work, so we can yield the control of the current thread being executed to some other threads. Okay, cool. Now with Go, what we saw, it is also a compiled language. We basically means whatever Golang code you are writing. Okay, uh, okay, that gets compiled to a executable file. Now the executable doesn't directly talks to your OS. Okay, it has a runtime model that takes the binary code, okay, and maps it to different p threads. Now those p threads are taken up by your OS to get scheduled by your hardware threads. Okay, cool. So I'll just show you time difference between these three codes. Okay, so what I have done is, okay, I have created three instances, okay, of like CPP, Python and Go of the same program. What this code does is, we loop over 1 to 1 million. Okay, 1 million numbers, and per number, okay, let's say I is that number, we perform root over of 2 times I plus 1. Okay, so this is a compute bound task. Okay, so what we should see here is the time differences here. Okay, you will observe the CPP one is kind of the fastest. Okay, whereas in Python 1 it's kind of the highest time taker, whereas Go is acting in the middle. Okay, so I have created a make file that runs each of the thread block section five times in each of the program. Okay, and so that we will have a statistical measure with mean and standard deviation. Okay, so in each of the program, the work is being distributed among different threads. Okay, now different threads are calculating the I value for different i's. Okay, and they are just mapping the result to the same array. Okay, so if I run make run, okay, so first it runs the C++ one and you can see blazingly fast. Okay, so C++1, the mean time, if you see, it is 0.04 second. Okay, with 3 to the power minus let's zoom this, 3 to the power 3 times 10 to the power minus 4 as a standard deviation, which is pretty low, right? Cool. So the C++ one took 0.04 second, whereas in Python you are seeing, right, because of the GIL, not all threads can are acting parallelly. Okay, one thread is computing the value, okay, and then other thread is running, it is doing the execution for its I value. So it's happening like that, and with that we are getting a mean value of 8 seconds. Okay, whereas for Golang, okay, we are seeing the mean value of 1.21 second, which is kind of closer to C++. Okay, but I will say very far as compared to Python. Okay, so Go is on a execution speed level. Okay, so we have C and C++ as the fastest, then we have Golang. Okay, then we have Python. Okay, so in the next video, my idea is to tell you like how Python is, so how this popular library like PyTorch, TensorFlow, OpenCV, NumPy are bypassing the GIL to use Python for doing compute heavy tasks. Okay, so I'll show you that. But all this programming primitives that you're seeing here, like the use of channels and all that, okay, that we will be talking about in future videos. Like I will tell you like how each line of Go is being executed, and all the data types that we have in Go for distributed computing. So we will have all that topics covered in this series of lecture. Okay, so till then just stay tuned to this video series. Okay, and yeah, just stay hungry for education and stay healthy. Cool. Thanks. Bye bye.